quarter one, way back in August 2021. We have to get in the time machine and go back to 2021. We started out the year, if you will recall, doing density. We actually did the density of a golf ball lab. Density is equal to mass divided by volume. It's a ratio of mass to volume. It is dependent on how tightly packed the particles are. So it's basically math problems. If you have something that is, you're going to put things in water that float, they are less dense than the water. So something that's floating along at the top, whereas something that sinks to the bottom is more dense than water. And density is basically a property of matter. It is something that helps us to describe matter. All right, so let's work a density problem. Page 14 of your Rocket Red packet, if you want to follow along. Density, remember, is equal to mass divided by velocity. If you are solving, this first question is asking for mass, how am I going to get mass by himself in this equation? Well, I got to multiply both sides by volume, right? The question is, what's the mass of 12.47 cubic centimeters? Cubic centimeters is a volume, so that is the volume we're given. What is the density of oxygen gas? Well, we can look that up in a table, and I looked it up already for you. 0.00133 grams in 1 cubic centimeter. So now we just have to do the math. 12.47 times 0.00133. And we get 0.0166 grams. Now, question of significant figures comes up. Something else we did last fall. How many significant figures are in this problem here? Or in this given information? We've got 4. So we really need an answer to 4 sig figs. This only has 3 in it, but this is something that we can look up. So we consider it to have unlimited significant figures. So if I look back to my calculator, I should not have rounded to 6. I should have 0.01659. So I'm going to go back and change that. 0.01659. All right, that's one density problem. Another density problem, they are going to ask you to calculate volume instead of mass. Once again, page 13 and 14 of your red rocket packet, we have a question that says a substance has a density of 1.86 grams per milliliter and a mass of 37 grams. What is the volume? Okay, again, we can set up our equation. Density is equal to mass divided by volume. If we sub our information in, 1.86 grams per milliliter is equal to 37 grams divided by unknown volume. Well, how do I get volume out of the denominator? We want to multiply both sides by volume, right? That's going to give us volume, but now we have density, volume times density, V times 1.86 grams per milliliter is equal to 37 grams. Okay, how am I going to get volume by himself. I need to divide both sides by 1.86 grams per milliliter. When I do that, grams will cancel and we'll get an answer in milliliters. 37 divided by 1.86 gives me 19.89 milliliters. All right. Well, that has 4 sig digs, and I only have 2 over here, right? So I'm now going to round that to 20 milliliters, and I'm going to put a decimal there to make sure that that 0 is significant. We'll do significant digits here in a minute. Okay, another helpful thing. If you remember our triangle, if we put mass on the top and density in one corner and volume in the other, this is another way you can look at how to set up the problem. First question, we asked for mass. So if I cover mass up, what's left? Density times volume. And isn't that what we did up here? Density times volume. All right, the second question asked to solve for volume. If I cover volume up, I need to take the mass divided by density. And ultimately, isn't that what I ended up doing? So, easy thing to remember is to make the little triangle with mass on the top and density and volume on the bottom. Also, how do you remember that it's mass over density? Density is equal to mass over volume. It's like a broken heart. Or a mouse with a blindfold on. All right. Next topic. We're going to do some measurement. All right. So, first of all, we got to remember, when we are measuring in the metric system, we've got prefixes we use. We have our base unit of 1, and we have deca is 10 times that, hecta is 100 times that, and kilo is 1,000 times our base unit. So if we have 1 kilometer, we move our decimal 1, 2, 3 to the right, we would have 1,000 meters. Okay, so let me get rid of this, and we'll write our scale up at the top. We remember this, King Henry died, and this, I'm going to put U for units, unusually, drinking chocolate milk. Now, because we're in college chemistry, we're going to go beyond those basic units. So 3 more spots out, 1,000,000 times bigger than your base unit, we get to mega. And if we go 3 more times, or 1,000 times bigger than that, we get to giga. If we go 1,000 times bigger than that, we get to tera. Okay? Tera, giga, mega. I put too many spots in there. Kilo, our base unit. Milli is 1,000 times smaller than our base unit. And of course, we can get smaller still. We have micro, which is a Greek lowercase mu. And then 3 times smaller, or 1,000 times smaller than micro, is our favorite, the nanometer. And 1,000 times smaller than that is the picometer. Oh, it's just P. And then 1,000 times smaller than that is femto, which is F. Okay? So basically, when you're using the metric system, you just need to be able to go back and forth. And it's just on basis, it's a base 10, so it's easy to do. Okay? Let's talk about significant digits. Significant digits have everything to do with measurement. If you're making precise measurements, you want to reflect that in your calculations. So when we talk about significant digits, we're actually talking about precision in measurement. Okay? But the basic rules for counting significance, which have nothing to do with precision, are as follows. When you count significant digits, all non-zero numbers are always significant. Okay? All sandwich zeros are always significant. If we have placeholder zeros, however, they are not significant. So it just depends on what you're talking about, whether it's significant or not. Now, we can go through and explain why again, but there's an easy way to remember this, and then you don't have to spend a whole lot of time worrying about it. You can just use this handy-dandy method. If this is the Pacific and this is the Atlantic, you look at a number. If there is a decimal present, we start counting from the left or the Pacific side. We start counting at the first non-zero. Ding, 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 ding. Those guys are significant. What if we have a number like this? We start counting at the first non-zero, and we start from the left. Ding, ding. We have two numbers that we count. So that guy has 4, this guy has 2. All right? What if we have somebody like this? This guy, again, decimal is present. Ding, 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 ding. I'm dinging a bell every time I hit a significant digit. I have 4 dings. These two guys are significant because if I rewrite 9,300, this is 9300 over 10,000. Okay, if I take away that when I write, I don't need that number when I write it as a fraction, but I need these numbers because if I take those away, it's not the same value. It's less precise. So if there's no decimal present, if the decimal is absent, we start from the Atlantic side. There's no decimal there, so we do not count till we get to a non-zero. Nope, nope. Ding, ding, that has 2 significant digits. If I put a decimal in, like I did in that last density problem, now I have a decimal, so I count from the left side. Ding, 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 ding. All right, so let's try a few significant digits. I have 0. How many sig digits does that guy have? If you said 4, you are correct. Decimal is present. Don't count those. Ding, 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 ding. Now, how about this guy? How many you got there? If you said 8, you're right. No decimal, but there's a non-zero. So 1, we got ding, 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 ding. A lot of ding dings in here. All right. Let's give you another one. How many you got there? 5. You guys are pretty good usually with those numbers. It's these guys that get you. How many significant digits does he have? He has 2. We don't count these because there are no non-zeros before we get there. Okay? All right. That's enough of that review. You can look back at page 28 in the red Rocket Red packet, if you want to see that. All right. The next thing we talked about was matter. Matter is anything that has mass and takes up space. Okay? We can sort matter into pure substances and mixtures. A pure substance, if you reach into a pure substance and you pull out a particle, every time you're going to get the identical thing. That's what a pure substance is. That can be subdivided into elements, which are made of one type of atom, and compounds, which are 2 or more different atoms bonded. Now, we did ionic bonding in December when we talked about solubility, and we had ionic compounds that dissolved in water. And we just got done doing covalent bonding just in the last few weeks, and we had 2 or more nonmetals in this case bonded together. So that is important, those atoms being bonded. Okay? Mixtures are 2 or more substances, which means they can be elements, compounds, or both, that are not chemically bonded. Okay? Mixtures can be separated by a physical change. Compounds can only be separated by chemical changes. Okay? Next up is our history of atomic discovery. If we go way back in time, again, time machine, Democritus, C-R-I-T-U-S, ancient Greek, he's the first guy to kind of come up with the idea that there is an indivisible piece, and he gave us the term atom. Okay. Next up, we have John Dalton, early 1800s, who does some experiments and discovers that elements are made of various, or not discovers, but determines elements are made of one kind of atom. So all gold atoms are the same. Compounds are 2 or more atoms, different atoms, in fixed proportions. which is different from when we talked about compound or mixtures are always not fixed proportions. They can vary. All right. And just basically Dalton came up with early atomic theory. He said that the spheres, the atoms were small spheres. All right, indivisible. Next guy up, about 50 years later, 100 years later, is J.J. Thomson. Not 50, 100 years. And it's not a P in his name. Thomson did the cathode ray experiment, where he ran electricity through a tube that had been evacuated, and that electricity, you could see a beam of particles moving through that. And when he brought something positively charged up next to it, it bent towards the positive charge. And if he brought something negative up next to that, it bent away from the negative charge, which told Thomson that, first of all, atoms have smaller particles. Those smaller particles are negatively charged, and he called them corpuscles, negative corpuscles. Okay, his model was that the negative corpuscles were surrounded by a positive matrix because overall atoms are neutral. All right, he called it the plum pudding model, which for us it works better if you think chocolate chip cookie. All right, the next guy was Rutherford. Not too long. They're contemporaries. They worked about the same time. Rutherford's just a little behind him. Rutherford does the famous gold foil experiment, where he has a piece of gold foil, and he has a alpha particle that is firing particles at a piece of gold, and behind that gold, a thin gold foil, and behind that gold we have a detector, and there's detectors all the way around. So he fires those particles, and he expects them to all go through and just end up right there. And to his surprise, some of them end up over here and over here, like they bounced off something. And some of them go through, but they end up off the center, like they got pushed by something. So from this information, Rutherford decided that there must be a tiny positively charged center called the nucleus. And that nucleus, because these alpha particles are positively charged, that's why they got pushed away. And that tiny nucleus is then surrounded by empty space and electrons. So the atom is 99% empty space with a tiny solid center. So, what do we have now? Well, we know we have negative parts. We know we have positive parts. So let's determine what our particles are. We have protons, which are positively charged, have a mass of 1 atomic mass unit. We have neutrons, which do not have a charge and have a mass of 1 AMU. And we have electrons, which are negatively charged and have virtually no mass. So, all of the mass of an atom is tied up with these two guys that are found in the nucleus. protons and neutrons. If we add the protons plus neutrons, we get what we call a mass number. This is specific to an atom, one atom. If you're talking about a group of atoms, we talk about the average atomic mass. When we write something like carbon, we write our atomic number below. The atomic number is equal to protons, and then we write our mass number above, which is protons plus neutrons. Okay? Now, unfortunately, we don't just have one type of each atom. Each atom has multiple varieties. Carbon, you can have carbon 12, you can have carbon 13, and you can have carbon 14. Something like 99.9% is carbon 12, but there's enough 14 out there that we can use that for radioactive dating, and we get, we have isotopes, is what these are called. Isotopes are atoms with different, and you could either say different masses, or you could say, no, I'm not going to say or, I'm going to say different masses slash number of neutrons. Okay, just like one atom has a mass number, if you have a group of atoms, they're going to have an average atomic mass. The average atomic mass is the average of all the isotopes. But you have to take into consideration how many isotopes you have. If you think about grades, if you get all A's and you have one bad grade, that's probably not going to affect your grades terribly. But if you have grades, so you would multiply all your A's by 4, and then you would multiply a B by 3, and you add those up and divide by the total to get your grade point average. So 1B doesn't bring your grade point average down that much. But if you have a variety of A's, B's, and C's, your average is going to be lower. We have to take into consideration what we call percent abundance. So the percentage of each isotope, and we take that percent abundance times the mass number for each isotope, and we add all that together. So this is isotope 1, this is isotope 2. We add those all together, and then we divide by 100. Why? Because we're using percents, and percents are based on 100. Okay? That's how to calculate average atomic mass. And the only other thing that I'm seeing to discuss today, we talk about ions. Up here we had our symbols, our nuclide symbols, talking about what's in the nucleus. Well, we can also put a charge on there. If we have a charge, we put it in the upper right hand corner. So let's say carbon has a -4 charge. What does that mean exactly? Well, the charge is equal to the protons minus the electrons. We know carbon has a mass of 6. If we subtract electrons and we get -4, what minus 6 minus what will give us -4? Well, 6 minus 10 will give us -4. So if you have a carbon with a -4 charge, it actually has 10 electrons. Now, we talked about recently electronegativity and how atoms want to hold on to their electrons if they have a lot of them, and how they want to get rid of them if they have a large radius and it's easy to get rid of them. And that is what leads to ions. Sodium has one outer shell electron, and he has a pretty big radius. So he gives that electron away. When that happens, sodium has 11 protons, And when he gives that electron away, 11 minus 1 electron gives us a number 10 electrons, right? 11 electrons minus 1. So that gives us a +1 charge. Because remember, 11 minus 10 equals 1. And that's how we calculate our charge. All right, that will get you some information to get started with the first part of this worksheet review, final review. And I will be back during advisory, so if you need to see me during advisory, you can always leave me a note.